Hi, this is Bobak. In this video, I continue my discussion on mathematical induction from a theory point of view. First, I write the principle of mathematical induction in a slightly different way, and then write the principle of mathematical induction using the language of second-order logic. Finally, I will show that these two statements of the principle of mathematical induction are indeed equivalent. Okay, some of you might find the material of this video very trivial, but the reason that I am publishing this video is because I want to improve my own understanding about the subject. So if you think whatever I'm telling in this video is trivial, we can just simply ignore that. Okay, the first thing that I want to do is to slightly change the principle of mathematical statement that we had in the previous video. So this is the copy-paste from the previous video. The principle of mathematical induction, PMI for short, states like this. This is the version that we used in the previous video. Let Pn be a predicate involving a natural number n with the following properties. First, P of 1 is true. Second, for every natural number k, if P of k is true, then P of k plus 1 is also true. If this predicate enjoys these two properties, then I can immediately conclude that P of n is true for all natural numbers n. So that is the statement of principle of mathematical induction. We proved this using the well-ordering principle in the previous video. Okay, but now, before continuing my discussion, let me just change this statement a little bit. So yeah, these are so trivial, so I don't know what name should I give them. So if you don't mind, let me call it lemma. I don't have any better name for this. Okay, so I would say let P and Q be statements. Then the conditional statement if P then Q is true if and only if P is true. So if and only if P is true, then Q is true. Okay, so that's a very simple statement, but I want to use this statement over and over again. So I want to say that there is no difference between saying that this conditional statement is true or saying that if P is true, then Q is true. Okay, so let me, even though I know this is very trivial, but let me just go through to prove this, okay? So the first one, I want to go to I'm assuming that let P and Q be statements such that this statement is true. If P then Q is true. Now we show that if P is true, Q is true as well. This finalizes the first part of this theorem, this lemma. Okay, assume that this is not. If not, then P is true, but Q is false. And therefore, if P then Q is false. And that is the contradiction, yes? Because I am assuming that if P then Q is true. Okay, now the other way around. And now we assume that if P is true, then Q is true. And we show that if P, then Q is true. Okay, assume that this is not the case. If not, if this is not the case, that if P then Q is true, then it means that there is only one possibility for that. And that possibility is if not, P is true, but Q is false. And that's also again a contradiction, because here we know that if P is true, then Q has to be true. Okay, so this is something that we use it over and over again here. So if I want to show that a conditional statement is true, it's enough to show that Q is true if P is true. Okay, now using this, I want to change the form of the second statement here slightly. I want to write it in a slightly different way. Okay, so instead of saying if P of K is true, then P of K plus 1 is true, I can write P of K conditional P of K plus 1 is true. Yes, that's exactly what I have shown in this lemma. So instead of saying that P of K is true, then P of K plus 1 is true, I can simply write the conditional statement P of K, then P of K plus 1 is true. Okay? Okay, so what I do is this. Let me write it here. So instead of number 2, so let me write it here. I would say that for all K in the set of natural numbers, the conditional statement P of K conditional P K plus 1 is true. Okay, so this is not something new. This is exactly the same version of the principle of mathematical induction we learned in the previous video. I didn't touch this one at all, but I changed this second statement slightly and wrote it in this way using this lemma. Okay, now I will call this one so let me summarize this here. I will call it PMI. I would say let us call it version A. Yes. So it means what is the content here? P of n is a predicate. Of course, I'm assuming that n is a natural number. Let me not emphasize it over and over again. And then we have two properties. Number 1, P of 1 is true. Number 2, for all K in the set of natural numbers, the statement is true. Then Pn is true for all n in n. Okay, so that is the version that we have in the previous session. The only thing that I have changed here, I actually used the content of this lemma to rewrite the second statement. Okay, but another way of expressing the principle of mathematical induction is using second order logic. So second order logic, it means that I can put a predicate under a quantifier. Okay, so in principle I would say that for all predicates Q, okay, if Q1 and for all K if QK then QK plus 1, okay, and then I will have for all n in n. So if you don't mind, let me write it precisely. So here I would write for all K in n, Yes, and then I would write this here. Okay, so that is the statement usually you see when you write the principle of mathematical induction using the second order logic. So this is actually telling you that, so by the way, this principle of mathematical induction claims that, asserts that this statement is a true statement. This tells you that whatever you choose as your predicate, if Q of 1 and this statement, then this implies for all n belonging to the set n Q of n. This statement is true. This is what principle of mathematical induction asserts in the language of second order logic. Okay, but I want to make it a little bit shorter so that we can, and the reason that this, by the way, is called the second order logic, because you are using the quantifier on the predicate itself. Okay, so to avoid this confusion, to make the discussion a little bit simpler, so let me avoid writing this by saying this. So I want to write something like this. I would write principle of mathematical induction version B. Again, I assume that Q of n is a predicate. Then the following statement is true. What is the following statement? The following statement is that Q1 and for all k in n, Qk, then Qk plus 1, again, then all of them in pair brackets, okay, so this is actually more precise and I think shorter. Not more precise, because I will show that they are actually equivalent. But this is another way to express the principle of mathematical induction. This tells you that as soon as you have a predicate expressing something about the natural number n, the following statement is a true statement. Okay? So it's a very nice thing. So you can imagine it in this way. PMI version B is some kind of a tool, or I don't know, a machine, that whenever you provide an input for the machine, the input here is a predicate regarding a natural number, then using this formula, this machine generates a true statement for you. Okay? So this is also another way of expressing principle of mathematical induction. So now I want to discuss a little bit about this in detail so that you can understand what's going on. I would say that I think it's instructive to prove this in this form using the well-ordering principle as we did for the principle of mathematical induction version A. Okay, so let me just do the proof here, because I want you to see what are the minor differences if we want to do the proof here. So let me write here proof using WOP, well-ordering principle. So what I know that Qn is a predicate, and I want to show that this statement, which by the way is a conditional statement, so this is the premise and that is the conclusion. So you see, this is a conditional statement. I want to show that the conditional statement is true. Do you remember the lemma here? If I want to show that P, if P then Q is true, I can show instead that if P is true, then Q is true. I want to use this lemma here again. Okay, so let me write these things in detail. Okay, so to prove this statement is true, to prove that this statement is true, okay, we show that if the premise is true, then the conclusion is also true. We show that if the premise is Q1 and is true, then the conclusion is true. Okay? Assume that this is not the case. And the premise is true, but the conclusion is not. Okay? So, I want to show that if this is true, this is also true. Assume that this is not the case, so I assume that the premise is true, but the conclusion is not true. But the premise to be true, because premise is written as a conjunction, it means that the first one and the second one components are true. So therefore, Q1 and for all k in n, Qk then Qk plus 1 are true. And when you say that this is not true, that for all n in n, Qn is true, so it means that this statement is false. So it means that and there exists an n in n, so that Qn0 is false. Okay? Now, I will follow the same proof as before. Let A be the set of all natural numbers such that Q of n is false. Because we realize that Qn0 is false, therefore, so let me write it in this way. Q of n0 is false, okay, and n0 belongs to n, so this implies that n0 belongs to A, so this means that A is not the empty set. And now I know that A is not the empty set, and I know that A is a subset of n, so by well-ordering principle, I can conclude A has a minimum. Okay, so I would say let little a be the minimum of A. So when you say that A is the minimum of A, what you can conclude that A belongs to your set, so it means that A belongs to A and Q of A is not false. Yes? Oh, wait, sorry, Q of A is false. Okay, so this is again what I will need later. Okay, but now we know that Q1 is true. Here we know that, therefore Q1 and this statement are true. So Q1 is true, so this implies that A is not equal to 1. And since A is an integer, so A is a natural number, so this means that A is greater than 1, so it means A minus 1 belongs to n. On the other hand, we know that, you see, this part of the proof is exactly as before. A minus 1 is less than A, and we know that A is the minimum of A, so this implies that A minus 1 does not belong to A. But we know that since A minus 1 is a natural number, the reason that A minus 1 does not belong to A is because this A minus 1 violates this part. So it means that Q of A minus 1 is true. Okay, so this is something that we have here. But look, here I know that this is conditional is true for all choices of k from the set of natural numbers. Okay? And now I know that, so a minus 1 belongs to n, and I know on the other hand that for all k in n, qk then qk plus 1 is true. So this implies that qa minus 1 then qa is true. Yes? Because I am telling that these conditional statements are true when I choose a k from the set of natural numbers. So if I choose a minus 1 for k, then this becomes q of a minus 1, then q of a is true. Okay? Now what I have, I know that q of a minus 1 is true here. And I know that q a minus 1 then q of a is true. So from these two, what can I conclude? I can conclude that q of a is true. Yes, because if q of a is not true, because the premise is true, the whole statement should be false, which contradicts that this is true. So it means that q of a is true. And then again you see the same contradiction here. So you see that there are very minor changes in the proof when I change when I want to look at this second version of the principle of mathematical induction using the second order logic. Okay, so let me just make it short. So that's a contradiction, so this cannot happen. Okay, so this is good to see, but now what I want to do here, I want to show that these two versions are actually the same. They are equivalent. Okay, so let me take these two versions with me to the next page. So let me go there and pick up this version A. Copy. So let me take it with me here. Yes, I can make it a little bit smaller so that I have enough space for the second one. And now I go here. Yes, so we don't need to make it so small. Yes, I can put it here. Okay, so now I want to express a theorem here that these two are actually indeed equivalent. Okay, this is that part that I am saying if you find it trivial, you can just ignore this video. But I think it's good to see how we can prove this in detail. Okay, so let me write the theorem. The statement of the theorem is simple, so I would say that PMI version A is equivalent to PMI version B. Okay. Okay, so let me first prove from left to right. So proof, I want to go in this direction first. So I'm assuming that principle of mathematical induction version A is true. I want to show that principle of mathematical induction version B is also true. Okay, so how should I do that? I would say that let me change my color. So let Q of n be a predicate. Of course, predicate regarding the natural numbers, okay? We show that So we show that this is true. I want to show that this is true. And let me call this one M, not to repeat. We show that M is true. Okay, so what I'm trying to say is that I am assuming that principle of mathematical induction version A is true. I want to show that principle of mathematical induction version B is also true. So what does it mean? It means that I need to choose any predicate Q of n, and regarding the natural numbers, then I want to show that this statement, which I call it M, is true. Yes? This let me write it in this way, is true for this predicate. But what I have as a tool in my hand, I can only use the principle of mathematical induction version A. Okay, but we just learned to show this, we show that if Q1 and for all k in n, Qk then Qk plus 1 is true, then for all n in n, Qn is also true. Yes, that's exactly the lemma. If I want to show a conditional is true, I need to show that the conclusion is true if the premise is true. Okay, now since Q1, so let me write it here, Q of 1 and for all k in n, Qk then Qk plus 1 is true, both Q1 and for all k in n, Qk then Qk plus 1 is true. Okay? Are true, sorry. So Qn satisfies conditions 1 and 2 of principle of mathematical induction version A. Therefore, the conclusion is also correct. So therefore, Qn is true for all n in n, or equivalently for all n in n Qn is a true statement. Okay, and we are done. Now we want to prove the other direction. Now suppose that Pn is a predicate such that P of 1 and for all k in n, P of k then P of k plus 1 are true. We show that, of course, let me write it as an illumination. We show that, of course, using principle of mathematical induction B, that Pn is true for all n in n. This is my goal, okay? Okay, since Pn is a predicate regarding the natural numbers, okay, then PMI version B implies that the following statement is true. So P1 and for all k in n, P of k then P of k plus 1 for all n in n, P of n. So because we have a predicate, the second version, PMI version B, guarantees that if I provide a predicate for this version of the principle of mathematical induction, it will generate a true statement for me using this formula. So then I have to admit that this statement, this conditional statement, is a true statement. Okay, again, I know that a conditional statement is true. This is equivalent to saying that if this is true, then this is also true. Okay? Sorry, so let me repeat it again. So I know that this conditional statement is true, but I know that the premise is true. Why? Because I know that Pn is a predicate such that P1 and this statement are both true. So it means that the premise is true. On the other hand, the whole expression is also true. So this means that the conclusion should also be true. So therefore, for all n in n, Pn is a true statement. This means that Pn is true for all n in n, as we wanted to show. Okay, so I hope that this video has been useful for you. I don't know, some of these proofs might seem very trivial, but as I told you, I wanted to have a better understanding between the connection that we usually use, because usually in the literature, most of the time, you will see this version of the principle of mathematical induction, and this is the way that in practice we use it. It's easier probably for our brain to use this version. But this is also a version that in second order logic people use. And I want you to have a better understanding of this very formal way of writing principle of mathematical induction. And then I want to show for you that these two principles, these two versions of the same principle are actually equivalent. Okay, so hopefully this video has been useful for you. Below this video I will put the link to the PDF file of these notes if you think that this is useful and you want to have them. Until the next video, be safe and goodbye.